Hello guys, today we will see the quantity of coolant required. As we seen in the last lectures, how to how dissipate the heat from electrical machines, and as well as we seen about the different methods of cooling and ventilations. Coolant required, it is a important thing related with heating, cooling and ventilation. So today we are going to knowing the power loss to be dissipated and temperature rise of the cooling medium. It is possible to calculate the amount of coolant required. Capital Q is nothing but heat loss to be dissipated in kilowatt. Theta, temperature rise of cooling medium in degree Celsius. Theta I, inlet temperature of cooling medium in degree Celsius. Capital H, barometric height in mm of mercury. Let's see quantity of air required. Let us first calculate the quantity of air required as a coolant. First we have to go with the specific heat of dry air at constant temperature. Cp is nothing but specific heat. Cp is equals to 0.2375. This value indicates the specific heat of dry air, which is standard value which cannot be changed. It is in calorie per gram degree Celsius. 1 calorie is nothing but the 4.18 joule. Just convert it into joule first of all, and joule is nothing but the watt second. 1 calorie is equal to 4.18. That's why multiply with 4.18, it will be converted into watt second per gram degree Celsius, and by dividing it is 1000, it will become kilowatt second. So finally you will get 0.993 kilowatt second per kg degree Celsius, which is nothing but specific heat of dry air in kilowatt second kg per kg degree Celsius. Next, volume of 1 kg of dry air at NTP. NTP is nothing but normal temperature pressure. Normal temperature is nothing but 273 degree Kelvin, and H, normal pressure, H is equals to 760 mm of mercury, and volume of 1 kg of dry air at NTP is nothing but 0.775 meter cube. It is nothing but a volume. By applying the Kelvin's law of pressure, that is P1 V1 upon T1 is equals to P2 V2 upon T2. From this balance equation, we can calculate volume of dry air required. So volume of 1 kg of dry air at actual working condition, that is H mm of mercury and temperature theta I degree Celsius, is nothing but 0.775 into 760 upon H into 273 plus theta I upon 273 in meter cube. Actually this is found from the Kelvin's law. We have to calculate the V1, so just adjust it for V1. You will get V1 is equal to P2 V2 upon T2 into T1 upon P1. So this is nothing but the value of P2. This is nothing but value of P1, 760 upon H, and this is nothing but the value of T1 and divided by T2. T2 is nothing but 273. As per we can calculate by putting the value of H, we can calculate the volume of 1 kg of dry air at actual working condition. So let us calculate the volume of air required for cooling or circulating in meter cube per second. How to calculate? Simply now heat carried away by air per second is nothing but weight of the air per second into specific heat into temperature rise. So just put the values. Specific heat should be in kilowatt second per kg degree Celsius, what we calculated. So we can define it as Q, that is heat carried in kilowatt, is equal to VA. VA is nothing but the volume of air in meter cube per second required to be circulated, divided by volume of air in meter cube per kg, into specific heat into temperature rise. Just putting the values previously calculated, VA as it is 0.775 into 760 divided by h into 273 plus theta upon 273. This is the volume of 1 kg of dry air at normal temperature, normal pressure, into 0.993 is nothing but specific heat of dry air, theta, temperature rise, and just simplify it. By simplifying, you will get 0.78 q upon theta. How it is getting? Just this is the formulation of q. Just adjust for VA, that is volume of air, dry air required to circulate. Adjust for VA, you will get that VA is equals to 0.78 q upon theta into 760 upon h into 273 plus theta upon 273. Just you can observe that I will give a hint for further calculations to solve the problem also. Here VA is equal to, first term is nothing but 0.775 q upon 0.993 q. Here 0.775, it is nothing but pressure. You can observe here, it is nothing but the volume of 1 kg of dry air at normal temperature pressure, that is nothing but the 0.775. This is for air. If it is with any other gases, you can put the volume for 1 kg of that gas, you can put at instead of 0.775 and divided by 0.993. It is nothing but the specific heat of the dry air. So for any other cases of or any other gases, you can put here the specific heat of that gas, particular gas. So you can change it for any other gases also, as we will see in the next. Now in general, for any gases medium, V gas is equal to, you can see here other parts of the right hand side of the V gas is as it is, just here substituted, instead of 0.775 it is capital V and divided by Cp, that is volume, that is ratio of volume for 1 kg and specific heat. As per this, you can also calculate for other gases. Now fan power required, you can also calculate the fan power required. PF is equals to P into VA upon eta, that is efficiency, into 10 raised to 3, that is in kilowatt. PF is nothing but quantity of air supplied by the fan, and P is nothing but a pressure of fan, pressure by a fan in Newton per meter square, and eta is nothing but the efficiency of that fan. So by putting the value of, you can also get the fan power required. Next, quantity of hydrogen required for, as we seen previous part, here also you have to calculate with Cp for hydrogen is standard 3.4 calorie per gram degree Celsius. As per the previous, again you have to convert it into kilowatt second per kg degree Celsius. By converting it, you will get the 14.21. And volume of 1 kg for hydrogen under at normal temperature and normal pressure, that is equal to 11.3. As we seen earlier, instead of 0.775, 0.775 is nothing but the volume of dry air, and for hydrogen it is 11.3. By putting the value of 11.3, you will get the equation 11.3 into 760 upon h into 273 plus theta I upon 273. This is for 1 kg volume required. And next we can calculate the final amount, that is 0.8. How it is coming? 0.8 is nothing but the ratio of volume for 1 kg divided by specific heat. Volume for 1 kg is nothing but 11.3 divided by specific heat is nothing but 14.21. If you are taking the ratio of that, you will get the 0.8. The remaining part as it is we have calculated earlier. So let's see quantity of water required. Quantity of water required for the specific heat of water is nothing but 1 calorie, that is nothing but 4.18 kilowatt second per kg degree Celsius. So directly we can calculate quantity of water required for the loss of q kilowatt and the temperature rise of theta degree Celsius, that is nothing but q upon 4.18 theta kg per second. You can convert it into liter per second. So VW, that is volume of water required for circulating, that is 0.24 Q upon theta liter per second. The quantity of oil required, that is nothing you can define with VO, that is quantity of oil required. VO is equals to 0.24 Q upon 0.4 to 0.5 into theta. You have to define the value of Cp, that is in between 0.4 to 0.5. For specific oil you can define it with a particular data sheets. If you don't know, you have to choose it between 0.4 to 0.5. Let's see the problem on that. Simple problem. Find the amount of cooling air required per second at the inlet temperature. That is, inlet temperature is given, that's 25 degrees Celsius, and the rating of that alternator is nothing but 25,000 kVA working at full load. The efficiency is 96% and power factor 0.87. Temperature of the air coming out of the machine is 50 degrees Celsius. Assume suitable values for specific heat and density of air. Air pressure is 760 mm of mercury. So go for solution. Simply you have to follow the last equation, that is 3.29. We will just see what is the equation 3.29. 3.29, this equation VA is equals to 0.78 upon theta into Q into 760 upon H into 273 plus theta I upon 273. So just follow it. For that, first of all we have to calculate the Q, that is loss. How to calculate it? We know the efficiency. Calculate the output power in kilowatt, that is equal to kilowatt is equals to output power in kilowatt is equals to kVA into power factor. We can calculate. So you will get the output power as 21750 kilowatt. Now we know the efficiency, we know the output. Just calculate the input value. Input is nothing but efficiency is nothing but output upon input. As per this formulation, input is equals to output upon efficiency. Just put the value of output and efficiency. Output is nothing but 21750 and efficiency is 0.96. By calculating, you will get the input value. Now calculate the losses, because we know the inputs, we know the output. Just take the difference of that. In input minus output, you will get total losses, that is nothing but the Q. Now we are going to use the equation 3.29 here, which is nothing but quantity of air required in meter cube per second. So VA is equals to 0.78 Q upon theta into 760 upon H into 273 plus theta upon 273. So by putting the value of Q and theta here, Q is nothing but 906.25, that is losses, and theta is nothing but the difference between the internal temperature of the machine and the inlet temperature of the air, that is 50 minus 25, and theta is nothing but the inlet temperature, that is 25 degrees Celsius. By putting this value, you will get the 30.86 meter cube per second. It is nothing but that amount of air is required to circulate and to dissipate the temperature. So thank you for listening to me. Thank you very much.